MotionV2V, editing motion in a video. Suppose that we have a video of two dogs, a Bichon and a Corgi, and right now they're tied. What if we could make the Bichon win? Using our editor, we can make that happen. But what if we want the Corgi to win? We can do that too. We call these video-to-video motion edits, and they're distinct from other kinds of edits because they don't have to maintain structure. So V2V motion edits can move objects. They can choose where things happen. They can choose when things happen by controlling time. And they can control the camera so that you can see the video from another angle. So here's a simple example. Suppose that we have this film strip. We have a man who roasts a marshmallow and then eats it. And what if instead of him eating it, we wanted the dog to eat it? We need a few things to happen. We need the marshmallow in the middle to be raised up more. And at the end of the video, we need the marshmallow to be towards where the dog would eat it. And of course, at the last frame, we need the dog's head to be in a different place, so we need the dog's head to move up here. We can express this edit as a motion edit. So if we want our AI model to do that, we have to tell it that somehow. And so we can think of this as before and after trajectories. The before trajectory, in yellow, tells you where the marshmallow was before the edit. And this purple trajectory tells you where the dog's head was before the edit. And you'll note that the dog's head is in the same place at every frame, which is why it's just a straight line. We also have our after trajectories, which is where we want those things to end up. So, as we showed before, we want the marshmallow to be lifted up and moved to the right, and we want the dog's head to be moved up more, which is why we have this trajectory and this trajectory. So we're going to separate these out into different images. We have our before video, and we have the after tracks. So we have our before video with the tracks that we start with, and we have where we want our tracks to go in the video below. Let's clean up the visualization a little bit and get rid of those lines and turn them into blobs. This is what the input to our video model looks like combined with this. So after running our model with diffusion, conditioned on these channels, eventually we'll create a video that looks like this, where the guy holds the marshmallow up and it doesn't get roasted and the dog eats it. So let's take a look at a real example, the same one that we saw before with the Bichon and the Corgi. So in the input video, they tie. So let's see if we can make the Bichon win. Let's use a motion edit. There's the output video. So the first thing that we do is we initialize some tracking points. So let's say we initialize a point on the Corgi's snout. We want to grab that point, and we want to move that point. After we've tracked the Corgi's snout, we're going to edit that trajectory. So let's put the Corgi behind the Bichon. we grab that trajectory and we move it further and back in time. And this causes the corgi to lag behind. Now, in reality, we need more than just one point to make sure that the background stays the same. Otherwise, this could be explained with a camera edit, for example. So we're going to add some stationary points. Points that are not changed, where we don't change the trajectory. So take a look at points 1, 3, and 6. And so 2 is the only one being changed, but we have more points now. And all of these put together is how we successfully edit the position of the corgi. So here's the input and output side by side. Now, one thing I wanted to point out is that this power pole wasn't shown in the beginning of the video, nor was this shadow on the grass over here. So yeah, you'll notice that in the first frame, you can't see that power pole and you can't see that shadow into the grass. But as you play both videos, that content is preserved through the edit. And that's what makes our video editor a true motion editor. By taking information from the entire input video, we can reveal things that weren't visible in the first frame. By contrast, our baselines, which are based on image to video plus motion control, are not able to do this. This power pole and that shadow are nowhere to be seen. And despite the quality looking generally worse, this is something that I think is important to point out because it's a fundamental limitation of that method. So let's take a look at another example of a swan. We're going to zoom out and freeze the camera. In the input video, the camera follows the swan as it sails down the river. And in our edited output video, you'll note that the camera actually stays still. So, like before, the first step is to add some tracking points to the swan. And after we've added those tracking points, it's time to edit them. We're going to make the swan a little bit smaller. And we're going to drag it so that it moves across the image instead of staying relatively stationary. Like before, to make it actually work, we're going to need more points. So we're going to add some points onto the background. And more points on the swan. Note that some points, like point number 15, momentarily disappear as the swan passes through them. When a point disappears, it means it's been occluded or isn't visible. This is an important input cue for our algorithm. So that now that we've used this to fix the camera in place, this is the full edit that we need to make to zoom out from this one. And so here they are side by side. Although, something I'd like to point out, even tiny details remain the same. So even though point number 10 is in a different place in both of these videos at a different time, it's still relatively close to this weed that was hanging off the side of the concrete. I2V models just wouldn't be able to do this because every single frame in the video is different. Any model that requires any part of any frame to be the same won't work with this type of edit. Our architecture is relatively simple. We use CogVideoX I2V as our base model and create an adapter. We have a control branch which is duplicated from the original model up until block 18, and we zero initialize MLPs to connect the DIT blocks of our control branch to the denoising DIT. We concatenate 3 extra channels into this control branch, one with our counterfactual video, which is another way of saying our input video, one with the control input dots, which track the before tracks, and one with the target tracks, which tell us where we want each one to go. They're all color-coded so that yellow pairs with yellow, red pairs with red, and blue pairs with blue, etc. And after denoising, we get an output video. In this case, we make the judge enter from the right of the video instead of the left. To train this model, we need pairs of real videos and motion counterfactual videos. A motion counterfactual is a video that has the same scenery, the same objects, the same appearance, and the same semantics, while differing only in motion, which includes timing, the camera, a different video speed, or an object moving in a different way. And they must be both jointly trackable. So there must be some way to create point correspondences between this input video that comes from our dataset and the motion counterfactuals, which we have to make somehow. Here's an example. In this pair, we have a man walking through the street. And on the left, he doesn't do much very special. But on the right, we make him twirl around. Note how the background is still the same. We still have that yellow taxicab. We still have that black sedan. We still have the same buildings and the same man. And the only difference is that he moves a little bit differently. This is why we call this a motion counterfactual. Using pairs like this, we can train our model. But how do we actually get these motion counterfactuals? Well, we derive them from our dataset. So suppose we have this video from our dataset. To create a motion counterfactual from it, the first step is to copy the first and last frame from our dataset video. By doing this, we can initialize tracking points in the same places. But we still need some content in the middle. So by using an LLM to create a prompt with new motion semantics, such as making him twirl, paired with a first-last frame video diffusion model, we can create new frames to fill in the middle differently. So now you can see him twirling. And so we're going to initialize points randomly from both the last frame and the first frame. Because these are the same image, we can initialize the points in the same place. But their trajectories will be different. After we have our trajectories paired with counterfactual videos and dataset videos, we choose a random subset of frames, a random contiguous subset, so that they don't always have the first and last frame in common. This gives us true motion counterfactuals that preserve the same semantics and yet have different motion. As we mentioned before, although it's a very simple and easy to use interface that doesn't require any segmentation and only uses point control, it allows for several different types of edits. It allows us to move objects. It allows us to control when objects appear and when things happen and how fast they happen. And it also allows us to control the camera. So here are some examples of that. Here we have an object control. So the hand symbol indicates that we're going to demonstrate moving an object. And in this case, we're moving the cat. As the fish stays the same in the fishbowl, we only move the cat. In this example, we move the swan. But actually, we're not moving the swan. We're only moving the camera. And we're changing when the swan appears in time. If you were to pause this video at any given frame, you'll notice that this yellow region is next to the bird's beak over here, and it's also next to the bird's beak in the output video. This is because only the camera has changed. And simultaneously, in the first frame, the swan isn't even visible. So this is also a time control edit, because we're controlling when things are revealed. In this case, we're saying that the swan is not visible in the first frame of our output video, even though it is visible in the first frame of the input video. And we can also just control camera movement in general, for example, zooming into these ducks. We have many more examples, so please scroll down and take a look at the supplementary website. We ran a user study comparing our algorithm to several different baselines. Spoiler, we won by a landslide. Baselines that require you to share frames just won't work as well. The judge is not visible in the first frame of this video. So any baseline, regardless of how powerful the base model is, won't be able to create the same judge that was revealed later in the video. The same problem arises when you try to control camera motion. When you control camera motion, often every single frame of the output video will be different than the input, which makes it impossible for any first frame video method to work correctly. So, for example, this one has no frames in common because there is no frame in the input video that was zoomed out by this much. And as a result, our baseline, in this case ATI, messes up badly. There's no way to communicate to ATI that you would like this to be zoomed out at every frame, including the first, which positions our editor as a first of its type. And again, please see below for many more examples, and thank you for taking